Okay, so we are discussing electric potential due to a spherical non-conducting sphere. So we have a spherical non-conducting, right? That means charges are distributed over the volume distribution charge is there. Field we have already derived. Let me write the field. So last class we have derived, and let us say the radius, this is center and radius is r. So for point less than r, inside points, field is k cube by r cube, into small r. Okay, similarly field and even equality can be applied here. Field for outside point, even we can apply equality. So field is k cube by r square. This is the field. Okay, so this result is there, we know that we have derived using Gauss law. So now we will use the formula or relation, electric field dv is equal to minus E dot dr, dv is equal to minus E dot dr. Using this relation we will derive potential. We want to find out potential. Gauss law I think we will discuss again, because I have used Gauss law here, but again we will discuss that in more detail. Okay, so let us try to use this. Let us first try to find out for inside points which are inside. Okay, so for inside points, if I take point anywhere inside point P, which is at a distance of r, how do we calculate the potential at that inside point? So what you need to do is, you need to, because what is the concept of this, when you integrate this one, you will get integration of minus E dot dr. But note that the field is different. If you draw the field graph versus r graph, field is a straight line up to the surface. After that field is going like this. So field functions are different, they are not the same function. So we need to break down the field into two regions. One is a straight line, another is this non-linear graph. So we want to move, you want to go from one point to another point, then you can calculate potential difference. But you know that potential at infinity is 0. We assume potential at infinity 0. So let us move from infinity to that point. We can move from infinity to that point. So let us do that. Move infinity to that point. So this integration which we are going to do is, we are going to do from infinity to that point where potential is V. And here infinity means potential at infinity, and potential at that point which is inside point, and this is infinity to that point r. Let us do that. So this is potential, final potential minus potential at infinity. This minus I will take out, integration. Note that infinity to r, as you are going, the graphs are different, so you have to break this function as infinity to capital R plus capital R to that is small r. So first of all you have to come to surface, and then from surface you go to the inside point. Directly you cannot go, because you are bringing a charge from infinity to the point which is inside this sphere. So you have to definitely cross this sphere. So you have to do integration from infinity to r, then r to small r. This integration you have to break it, and you know the field are going to be in opposite direction. Of course this minus will come inside. Otherwise if you want, you can keep a bracket here, you can take a bracket here. Okay, you can take this as a bracket. Inside the bracket you can keep. E dot dr means EDR, and you are going from here to here. So what is the electric field? What is the electric field? Hmm? Electric field for outside point. What is electric field for outside point? Because from infinity to r, electric field will be due to outside point, which will be kq by r square into dr. What about inside point? Inside point is a linear relationship, which is kq by capital R cube small r dr. This integration, now let us and potential at infinity 0. So this is what you will be getting. This term is anyway 0. So try to solve this. Here kq will come out 1 by r square, integration is minus 1 by r. And this integration is going from infinity to capital R. Plus here also this is kq by r cube will come. R integration is r square by 2, and this is going from capital R to small r. Let us try to do this. So this will come minus kq, and when you do integration you have to put minus 1 by r. Minus means plus 1 by infinity. This term come here, kq by r cube. Substitute 2 also take out. Substitute upper limit r square minus capital R square. Okay, let us try to solve it. So potential come as minus 1 by infinity 0, so it is minus kq by r plus, open this, kq by 2r cube into r square minus kq by 2r cube into r square. Open this. So potential is minus this r square, r will cancel out, and minus this and minus, so minus 3 by 2 kq by r will come, and this becomes plus kq by 2 r cube into r square. Now this minus, if you want to take inside, take this inside this minus, and things can be taken out. So kq by r you take out, and then you will see that it will be 3 by 2 minus r square by 2 capital R square. This is an important result. We have to remember this. This formula is for potential at any point inside the solid insulator sphere. Sphere is an insulator, charge is volume, charge distribution. kq by r 3 by 2 minus r square by capital R square. Okay, 2r square. This formula we must remember it. That's all. It's a very important formula. Now, what about potential for points outside? So we know that for points outside this, that sphere behaves like a point charge. Whole sphere behaves like a point charge due to symmetry. So for points outside the solid sphere, the whole sphere behaves like a point charge. So potential due to point charge formula we know, k cube by r. Simple, we can apply that logic. Otherwise, if you want to prove, you have to apply the same approach. Okay. So this is the formula for potential. This formula for potential r less than, even equality will hold. So for inside points we can use this. Now for points outside point, if you want, you use the same approach. So you are moving from infinity to this surface, or to any points outside you are moving. You are not moving inside, right? So let us say you are moving to any point here, and this point is at a distance of r, but this r is greater than capital R or even equal to outside. So now let us try to prove that. Same approach, formula will be same. dv is equal to minus E dot dr, and you have to integrate again from potential at infinity to potential at that point. This is from infinity to that point. So this will be V minus V at infinity, and this will give us electric field only outside, because you are moving only outside. So outside electric field is kq by r square. So this will be kq by r square dr. So do this two-step integration, do that. So this infinity potential is 0 here. So this will become minus kq. 1 by r square becomes minus 1 by r, and you are going from infinity to small r. So this calculation will give us V equal to minus plus kq by r. 1 by infinity 0. This is what is the formula for potential for points greater than equal to r. Even equal to we are including because it's a continuous function. There is no discontinuity. So we can use it. Now try to draw this graph. Draw this graph. It is a very nice graph. This function, we have to note that. So this is potential graph versus r, distance from center. So if you are considering, uh, let me just think about, like I am thinking that here it is like a circle, means sphere. You can think about it. So this point represent potential at the center and up to the surface r, and beyond that. Similarly, this side also, if you want, you can draw this graph. So when you substitute small r is 0, you will get this potential at the center. Small r 0 means 3 by 2 kq by r. So this potential which you will get 3 by 2 kq by r, this is the potential at the center. Now you will see that as you go away, r increases, it will decrease. So this graph is going to be different. And when you take r is equal to capital R, that means at the surface r is equal to capital R. So it will become 1 by 2, 3 by 2 minus 1 by 2 is 1. So you will get kq by r. So kq by r value will come at the surface somewhere here, this side also, this side also. So the graph will look like this, here also like this. Okay, this is the graph of potential. And also note that what is the differentiation. Try to calculate differentiation of that. Try to calculate differentiation of this. Try to find out differentiation. So differentiation, when you do, this term will become 0 and this term will become also, here you will get 2r by r. So slope is 0 only at here. You can see slope will be 0 only at this point. Slope means electric field. You can try that and check out. Is the slope 0 or not 0? Because when you differentiate potential, this is for points inside, dv by dr. Actually, what does the slope represent? Dv by dr represent electric field minus dv by dr. Okay. So this is the, here you can calculate the potential, but I think it will not be defined. It will not be defined. You can try to find out that. What about at the surface? And it's a very important thing to note that from here to here the graph is a parabola, and from here to here the graph is a hyperbola. So that means for points inside, this graph is a parabola graph. This graph is a parabola. After that, this graph is a hyperbola. Okay, this we should note. And this point within the parabolas at the center, this is maximum. So slope is 0 here. Slope is 0. You know that electric field depends on r. So when r is 0, slope is 0. So here the slope will be 0. dy by dx, dv by dr, that will be 0 here. Slope dv by dr is 0 here. Are you understanding this? Yes. Okay, very important graph. This formula you have to remember. This formula is for outside. That's why this, see, this V is 1 by R, na, that 1 by R is for this portion. This 1 by R graph, na, is for after this surface, this side. This is hyperbola. Sometimes they may ask it, very important question, where is the shape changing? Because see, this is convex shape, there is concave shape. Where does shape changes? For that you do double differentiation. Double differentiation you can do. Double differentiation you do for this point. Double differentiation, single differentiation will give one small r, and double differentiation, what does the double differentiation give here? Negative sign will come because minus r square terms are there. So when you differentiate 2r and then minus term, so double differentiation negative means this shape of the graph is here negative. Double differentiation negative means convex. And if you can try this one, here differentiation of 1 by r gives minus 1 by r square. Again minus 1 by r square will give minus positive will come. So positive means concave. So this is the point which is the surface. At the surface the shape of this graph is changing. This point is called point of inflection. Point of inflection. Point of inflection. That's all. I think this is what we need to know in this. So that's what important things I think we have covered. Solid sphere, hollow sphere, and all these important results are over. Right. What else is remaining? Disk already I think we have covered that. Done. So I think now Gauss law we can start. Gauss law we can start. Basic Gauss law we can discuss. Some applications we can discuss, and then you can work out problems. Okay. Then potentials afterwards you can start, because maybe in your school that potential will be starting next week. Okay. Then let us take Gauss law. What is Gauss law? Gauss law is a method by which we can find out electric field of symmetric charge distribution. Okay. What is Gauss law? It is a method to find out electric field due to symmetric charge distribution. Okay, symmetric charge distribution. Now first of all we'll understand what is Gauss law, and Gauss law requires the idea of electric flux. So first we'll try to understand what is electric flux. What is electric flux? Suppose that there is a electric field lines I am taking. There is electric field lines, and there is a flat area. Let us consider area. Area means it is like a flat surface, like this. Okay. So this is a flat surface, like some inclined, and for example take this, like this hook. Okay, it is like this way, inclined, right? Inclined, and electric field is going like this, horizontally. So how do we understand what is electric flux? So what is the meaning of electric flux? First understand that electric flux represent, its symbol is phi. phi E, electric flux represents the total number of field lines crossing a given surface. That surface can be open surface or closed surface. Here we are taking example of an open surface. This is your open surface. If it is a closed surface, then it will be like cube or cuboid or sphere or some closed figure. It is not a closed figure, it's like a face, that's all. Flat surface it is. So how do we find out, right? How do we find out that how many field lines or what is the value of field lines crossing here? This is the electric field. Okay. So for that, what do we do is, and note that crossing the given area means how much field lines is crossing, but we need to see how much field lines are crossing normally. Normally means perpendicularly. So what we need to do is we need to draw a normal here. This is normal to this, and let us represent area as a normal vector. Suppose this will have some area A. Area is equal to A, but that area, let us represent that area in this direction. Area we are representing in this direction, area vector. Normal vector is, let us say, unit direction is n cap, and cap is a unit vector along normal direction. So this area vector can be written as area into normal unit vector. So magnitude into unit, if you multiply, that will become a vector. So area vector is a normal area vector. So what is area vector here? This area vector is called normal area vector. Normal area vector. And note that this angle they will give as theta. This angle theta. So this is area vector. This is field vector. So you can try to take the component of field in this direction. So this is electric field here, and in this direction field will be E cos theta. E cos theta is the field direction in this. E sin theta component will be parallel to this surface. E sin theta. E sin theta field will be parallel to the surface. So E sin theta component will slide over the surface. E cos theta will become perpendicular to surface. So E cos theta you can take cutting the area perpendicularly, right? If you take a unit area, so for a unit area it will be E cos theta. For area A, it is A into E cos theta. So that's why the flux can be defined as, electric flux will be defined as E cos theta into the area, which can be written as E vector dot area vector. Are you clear about this? Yes. Okay. That is the way how to calculate it. But suppose if the surface here, note that the field is uniform and area is also like a flat surface. But what happens if the surface is curved surface, where field is not in the same direction, this angle will not be same. So in such cases, if there is a non-uniformity means either the field itself is non-uniform or the area itself is a irregular surface. In all such cases, we have to do integration. Let's take example. Here it is a direct dot product, but sometimes we have to do integration if the surface is not like that. For example, surface is a curved surface like this. Still it is a open surface only, but we are taking like some curved or irregular surface it is. And field lines, let us take field lines is uniform. field lines are uniformly cutting it. Okay, this surface is still a open surface only. The surface is still a open surface. Open surface. So how do you calculate? Then here everywhere field will be making different angle. How do you define normal? So in such cases, you first of all take any point area anywhere. Suppose here I choose a small point area. So this area vector will be coming outward like this. Like this area vector will be there. And here it is making some angle theta. And this is the direction of electric field here. So we will calculate a small electric flux here at this point. That small electric flux will be E dot dA vector. And then you can integrate it to calculate the total flux. You can integrate it. So you can integrate it. You can integrate it over the entire surface like that. This is how we can calculate. For non uniform or irregular structure, we can do that. Okay, but here one thing you have to note, very important. One thing note, for an open surface, the angle for a given open surface, the angle should be taken as acute. What does this means? Try to understand this. Suppose if I have drawn a flat surface, okay. Suppose the electric field lines are going like this way. Now when I say normal, I want to draw a normal. So normal I can draw, which direction should we take normal, because this is normal to this surface. Should we take normal in this direction or should we take normal which direction normal should we take? That is the question now. Because normal can be this direction as well. So area vector we can take this direction also. If you take this direction area vector, let us say if you take this direction area vector, then the angle between field and this area vector will be how much? Because this is the direction of the field, right? This is area vector. So this angle will become obtuse angle. Yes, correct. This angle become obtuse angle. So you should not take area vector this one. You should reject this approach. We cannot take this area vector. No. So which area vector? So no, because normal can have only two directions, either this side or that side. So we must take this side, because this area vector, if you choose, it will be making an acute angle here. Acute angle. So this we can take here. This we can take. This we should not take. That is the idea. So because for an open surface, it is both the possibilities are there. But for a closed surface, there is a fixed direction of normal. How? Let's understand that. For a closed surface, normal area vector is outward is along outward normal. Outward normal. What is this outward normal means now? Suppose for example I take a closed surface. Closed surface means I take a sphere. Let us say I take a sphere now. A sphere I have taken. So suppose I have to take area vector. Area vector I have to always take like this. If I choose here a small area vector dA, because surface is irregular, so I have to represent area vector like this way. If I take area vector here, then I have to take area vector like this way. So area vector will be outward normal. Outward normal. It cannot be inward normal, because inward also it can be, but it cannot be. It should not be. Okay. We have to always take like this. Electric field can be regular, irregular, it doesn't matter. Suppose electric field is uniform like this. Like this. Electric field. So idea is that wherever you have to do integration anyway, but when you are going to take any point, you have to take normal outward. Okay, this is what is the meaning here, how to take. For open surface, we have to decide which side is acute angle forming, that side normal will take. And once you have fixed this normal, you cannot change it. That is what it means. Now, now once you have fixed a normal for a surface, for example, suppose this is a flat surface, although this is a book of mass, but if it is like a flat surface, no, I have decided normal to keep like this, outward this side. So once I have decided normal will be this side, I cannot change afterwards. I cannot change afterwards. Once I fix it, it cannot change. That is the meaning. Okay. Okay, this is done. I think this is about electric flux. Now, let us take some important results on this. Let us consider important results. First point. Suppose field is uniform, electric field is constant. Constant means uniform. Uniform field. And I take a closed surface. If I take a closed surface means any type of irregular surface it can be. I can draw a sphere, cuboid, any type of irregular, regular doesn't means, but it is a closed surface. It is a closed surface. So a closed surface is kept in a uniform field. Field is parallel lines, uniform field. Uniform field lines are parallel. Okay, so if the field lines are parallel means uniform, equally spaced it is. Now if they ask what is the flux through this entire closed surface, what is the electric flux, or what is the flux of the electric field lines through this entire closed surface, then can you guess out how much flux will be there through this surface? Can we guess out? So think about what is electric flux means. Think about what is electric flux. Electric flux means the total number of lines which will be crossing through this surface, that's all. So if you see here, the surface, let us say 10 lines are entering. 10 lines are entering from this side. The same 10 lines are going outside from that side. Correct? Are you understanding? So basically, overall, there is no field lines is crossing, because whatever field lines are entering, same field lines are going out. Suppose if it is an open surface, then of course you can say that 10 field lines are cutting this. But actually, this closed surface is made up of left side surface, right side surface, right? Here you can see that this is made up of left side surface here, and it is also having the right side surface here. So whatever field lines are cutting or entering here, the same field lines will be going outside here from this surface. So effectively there is no flux. So flux we can say as zero. Net flux through the closed surface is zero. But if they ask what is the flux entering, that is not zero, because some lines are entering here. Let us say 10 lines are entering, or how much flux is leaving, it cannot be zero. So flux entering and flux leaving, they are not zero. Okay, so flux which is entering and flux cannot be zero, and flux which is leaving, that also is not zero. But the sum of this total entering and leaving, that is zero, because effectively whatever is entering, same is leaving out. So none of the field lines is effectively crossing. That is why it is going to 0. And you can also think about it why it is like that. For example, suppose I start thinking in a basic manner. Suppose if I take a small area vector here, small dA vector I will take, okay, and somewhere like this is tangent, no? Suppose this is tangent here. Try to understand this point. Suppose I am drawing a uh, tangent here like this tangent. This tangent I can slide. Somewhere same tangent will be there definitely. The same tangent must touch the surface exactly somewhere, right? It will touch it. Definitely at one place it will touch it if you bring it this side. Let us say touch. Okay, it will touch. And if you try to draw here area vector, dA vector, and here dA vector, they will be exactly opposite of that. This dA vector, that dA vector will be exactly opposite. And electric field here, electric field lines are always in same direction. So electric field line here is this way, here electric field line is this way. So note that this electric field lines, suppose it is making acute angle here, let us say that it is making acute angle theta, here it will be making pi minus theta, correct? Because this side this angle theta, that means this angle is same as theta. With the horizontal it is making downward, so this angle is pi minus theta. So if you try to take a small flux here d phi, that will become E dot dA, which will give us E dA cos theta, E dA cos theta. But when you calculate here the flux, here that is small flux, if you calculate d phi, that will be E dot dA here also, E dot dA is here also, but E dA cos of 180 pi minus theta, cos of 180 minus theta is minus cos theta, so minus E dA cos theta. That is what I was saying, entering and leaving. If this flux is entering, that flux is leaving. Some of these two opposite fluxes will cancel out. That's what happened. So because if the field is, because field is uniform, so it is cancelling out. Okay, because here field value E and their field value E are same, and this direction theta is also same, everything is same, so it is getting cancelled out, right? So in a uniform field, any closed surface you put, whether regular or irregular, total flux through that surface is zero, but flux entering will be there. Similarly, flux leaving will also be there, but the sum of flux entering and flux leaving, that is zero. Clear? Yes. Okay, next. Let us move to the next. But this result will not be true for a non-uniform field. Then what else? Now try to understand this calculation of flux through a spherical surface. Let us take a point charge. So now I think Gauss law we can first take. Let us take Gauss law. Gauss law, because flux is concept is clear. Now Gauss law we can understand. So what does Gauss law says that? Gauss law says that the total electric flux, total electric flux of a of electric field, total electric flux of, or total flux of electric field, total flux of electric field lines, crossing total flux of electric field lines through a closed surface, is equal to charge enclosed divided by epsilon naught. So what this law says that, suppose that there is a surface, closed surface, they are talking about closed surface only, closed surface, and let us say inside this closed surface there are some charges q1, q2, q3, some charges are outside q4, q5, q6. The total flux of electric field lines to a closed surface. So this surface is a closed surface, and the total flux, resultant flux, okay, that means what? Net flux through this closed surface. That net flux we can write as integration of E dot dA. But now there is a circle we will be keeping here. This circle represent integration is done over a closed surface. Okay, this total flux is equal to charge inside this surface, and this surface is known as Gaussian surface. Note that this is called Gaussian surface. Gaussian surface. So Gaussian surface, how much charges are there inside? Q1 plus Q2 plus Q3 here. Q1, Q2, Q3 divided by epsilon naught. Okay, this is what it is. This is the law. What does the law says? Law says very simple. Left hand side is equal to right hand side. What is left hand side? Left hand side means total flux calculation, which involves integration of E dot dA, which is quite complex because different places, different field lines will be there. Quite complex left hand side. But right hand side is quite simple. It says only the total charges enclosed within that surface divided by epsilon. Very simple. Right hand side is very simple. Okay. Now this is what is Gauss law. Let us try to prove this Gauss law using Coulomb's law. We can try to prove it. Okay, let us take that. Proof of Gauss law using Coulomb's law. This proof will also come in your board exam. Prove Gauss law. Okay. So what we are going to do, let us keep a point charge and let us draw a surface which is a Gaussian surface, which is equidistant and the radius is r. Okay. So this is a Gaussian surface I have chosen, or I have drawn a Gaussian surface. And I have drawn a Gaussian surface which is symmetric to the, because I can draw any regular surface, because Gauss law doesn't say that it has to be regular surface, it has to be closed surface, that's what it says. But that closed surface can be regular or irregular, but I am choosing it regular. Why? Because for my convenience, so that I can easily do the integration part, which is left side part, because left side part is not easy to do for a irregular surface. Okay, so we have conveniently chosen, because it is valid for any type of surface. So, but conveniently we are choosing it as a symmetric surface. Okay, what is the advantage of symmetry? There is an advantage of symmetry that we are going to use it. Let us see that. So suppose if we already know the field lines is going like this. We already know this fact. We know for field lines goes radially outward, we know already. Okay, so now let us try to do the integration part. So we are going to choose a small area and do, and note here very important thing is that the small area vector should be outward normal. We discussed that. So this dA here you take or here you take, everywhere it is going outward only. This dA is going outward, radially outward, and field is also going radially outward. Note that field is also going radially outward. Field is also going radially outward here, and very important point to note that the value of field at all these points is same because of symmetricity. The magnitude of field is same because each point is same distance from the center. Yes, that is what we have got advantage. So electric field magnitude is k q by r square. Simple. Everywhere on this surface, k cube by r square, and direction radially at what? Direction of area vector everywhere same. So the angle between them is going to be 0. So let us take small flux is equal to E dot dA, and let us try to calculate the net flux, which is the integration of this d phi, which is integration of E dot dA. Let us do that. So now while we are doing integration, E dA cos 0 degree, remember cos 0 degree 1 because they are in same direction. And note that electric field magnitude is same, so we can take out of integration very easily because it is constant. So basically you have to do what? You have to just do integration of the area, dA, total area. You find out area of a sphere, already we know that. But suppose if you would have taken irregular surface, then more problem would be there. Why should we put ourselves in problem? Let's not put ourselves in problem. Let us try to find convenient way of doing this. This is the convenient way. So area will be how much? Area of a sphere 4 pi r square over. Now let us substitute electric field. Electric field value we know that. Substitute that k q by r square. R square terms cancelled, and k value is 1 by 4 pi epsilon naught. Remember, 1 by 4 pi epsilon naught q, and this 4 pi also get cancelled. So we got the right hand side of Gauss law. We started with left hand side of Gauss law and we got right hand side. So we can say that the total flux integral of E dot dA through this closed surface is equal to charge inside by epsilon. This charge is charge inside. Only one charge is here in our example which we have used. Only one point charge. If there are many charges, then we have to add all those charges. Okay. So in general, this is the charge enclosed. Charge enclosed. Clear? Are you clear about this? Yes. Okay, so this is what is Gauss law over. Gauss law basic concept is over. Now Gauss law applications are, lot of applications are going to be there. Many applications are there. But only thing is that how to draw Gaussian surface, because we have to use the idea of symmetry. So let us try to understand symmetry. What kind of symmetry exists? Okay, let us try to understand symmetry. So here we should note one important thing, that Gaussian surface, Gaussian surface, which is a symmetric surface. It may be not be symmetric, but generally we are making it symmetric. We are using it symmetric surface for our convenience. So Gaussian surface or symmetric surface should not pass or cut a point charge. However, it can pass or cut charge distributions. What does that mean? That means suppose if there is a point charge here, you cannot draw a Gaussian surface passing through this type of Gaussian surface. This type of Gaussian surface is not possible. We should not take such Gaussian surface which should pass through a point charge. But suppose if there is a charge distribution, let us say that there is a rod. On this rod, charges are distributed. Then we can take a surface like, passing through this. If you want, you can choose like this type of surface. This is possible. This type of Gaussian surface is possible. We can choose such type of Gaussian surface. Just give me 1 minute. Okay, so let's continue. So I have to attend one call there. Okay. So we have discussed about this, right? Did you understand this point? We can pass the Gaussian surface through a charge distribution but not through a point charge. Okay, then let us move next. What else? So we should discuss about symmetricity. Symmetricity. There are different types of symmetricity. First symmetricity is like spherical symmetricity, which we are seeing here. Spherical symmetricity. Spherical symmetry. What is spherical symmetry? Charges are distributed like in a spherical sense. Spherical sense means we can have different types in spherical also. For example, here suppose if charges is like on a cell, for example, charges is present on a cell like this. So charges are present like this way on a cell, and if you want to make a Gaussian surface, how can we choose? We can choose Gaussian surface as a sphere with the same center. So you can choose this as a Gaussian surface, or you can choose this as a Gaussian surface. Why it will be symmetric? The reason symmetric is that this distance, suppose you to take this surface, right? So the distances from these surfaces are same, right? Everywhere it is symmetric, same distance it is. From the chart distribution, the distances are same, so you can choose that. Otherwise, if you are choosing this surface, then this inner surface also you can choose. This again same distances are there. So that is why you can choose this Gaussian surface, either this one or this one. So whatever you are going to choose this Gaussian surface, these Gaussian surfaces are spherical surfaces. They are spheres, and center is the same center. This is called symmetric, spherical symmetricity. Okay, then cylindrical symmetricity is also there. Let us understand cylindrical symmetricity. Cylindrical symmetry. Cylindrical symmetry means, like for example, some charges are distributed like this way on a cylinder, or not on a cylinder also it possible, but let us take a line charge, and particularly very long rod, then what happens is that you can try to make a Gaussian surface like this manner. You can try to make a Gaussian surface like a cylinder. Why cylinder? Because this is, note that this cylinder, for this Gaussian surface cylinder, this is like the axis. Okay, this chart distribution is like axis. So this should be the axis of this cylinder. Axis of cylinder. If this is the axis of this cylinder, then what happens? Each point on the cylinder is going to be equidistant. Note that each point on this let us say I choose this point. So this point is equidistant. I choose this point. Each point on this surface have same distance. Are you understanding this? Yes. Okay, so each point is same distance, we will have advantage, right? What advantage we will have? So you know the radial field lines are going radially outward here also. So field lines will be going like this way. So if this you take as electric field and area vector, same direction, right? Same direction. So everywhere same thing will be happening. Electric field and area vector will be same. Small area vector which you will take. But what about, we need to take a closed surface, right? So this cylinder is closed from top and bottom also. So top surface, if you see, top area vector will be like this way. But note that field lines are only radially outward. So here 90-degree angle will be there. So note that on the top surface, the field lines will be sliding over the surface. So field line will not cut. So what will happen? The flux of the top surface, this flux, here the flux, let us say called phi1. So phi1 will be 0. Flux of bottom surface is also going to be 0. So that means only flux will happen through this curved surface. So total flux of this surface will be phi1 plus phi 2 plus phi 3, but phi 1 and phi 2 has become 0, 0. So only flux will be flux through the curved surface, and curved surface flux will be again easy to integrate. That will be integration of EdA. Note that here you are not going to put a circle here. You are not going to put a circle here. Why are you not going to put a circle? Can you tell me? Yes. Why are you not putting a circle here? Why? Think about it, because we were putting circle for total closed surface, but phi 3 which you are calculating, it is not a closed surface because it is the curved surface of a cylinder. Curved surface is just like round that surface. Top surface, bottom surface, curved surface. So then when you combine all the three surface, then it becomes closed surface, right? Yes, that is why you are not putting that circle here, because you are calculating phi 3 for only curved surface, because phi 1, phi 2 is 0 anyway. Okay, so note that here this field will be constant and you will be taking out this, and basically you have to do the integration of this area. What is the area of this cylinder, curved surface area? Tell me. Let us say the length of this cylinder is L and radius is R. Tell me the curved surface of a cylinder. Curved surface of a cylinder will be what? Correct, right. So this will become E into 2 pi r l. 2 pi r l. Okay, right. Okay, so now see, now you can use this. Let us now do derivation of this charge distribution. Suppose there is, this is like infinite, right? So this is the flux, this is the total flux we were calculating. Now tell me Gauss law. Total flux, net flux is equal to charge inside, charge enclosed by epsilon naught. Tell me how much net flux we have already calculated, E into 2 pi r l. What is charge inside? Tell me what is charge inside this. This much length is inside this. This much length will, how much charge will happen? Tell me. Yes. Charge of length L. Suppose lambda is charge density, linear charge density. Yes. Tell me. Lambda is linear charge density, means charge per unit length. So L length will have how much charge? Yes, that's all. So lambda L over, game is over, LL get cancelled. You got the electric field line at some distance R. What is that? Lambda by 2 pi epsilon naught R. This is what it is. This you have already seen the proof of this. If you want, you can write in terms of K. So multiply 2. So 2 K lambda by R. Have you seen this proof? Infinite rod, remember, we have seen the proof of this. So this is what it is, right? So like that you will be able to prove that. So done, like this we can do that. So remember, for a last class for solid sphere, hollow sphere, we have used Gauss law. You can go through the notes. Okay, I will be also uploading the videos today. Okay, so that's what it is. So I think we are done. Application, these are all the applications of Gauss law. Now major application, fundamental application can come on the some important application of solid angles that we will discuss. Solid angle concept. So some concept related with that. First thing is that suppose if I take a point charge. So what happens is that the field lines are going radially everywhere. And also note that field line will start not exactly from that point. Can you tell why? Have you seen NCERT book? See NCERT book also. You will not see that the field line start from this. There will be a little gap will be there. See, I will draw that gap here also. There will be a gap here. This I am showing you the gap. Okay, there is some gap you will see. Field line will leave that gap and then it will start from that gap. Why that gap is there? Find out. There is a gap here. Charge is here, but there is a gap here. Why there is a gap? Think about it. Okay, so this is the field lines are there. Now suppose I am drawing a sphere. Okay, I'm dot a sphere I am drawing. This is the center of this. Now suppose if I take a portion of some sphere like this is a portion of a sphere, okay, portion of a sphere. On this portion of the sphere, there will be some field lines will be crossing through it, right? Because so many field lines are crossing. What will be the flux through this portion? If I ask what is the flux through this portion, how will you calculate? Remember, this is a three-dimensional surface. This is a three-dimensional surface, and this surface is not a flat surface. This is not a flat surface. Suppose if you want to understand this better, you may try to join these edges, and you can try to make a small disc here. Note that this I am making a disc here. This disc I can make. Then this is like a cone here, right? Can you see that? Yes. This is a cone. Are you able to figure out this one? But this curved part, which is a sphere, that is not the part of the cone. That is bulged outward. Okay. This is not, because this is a portion of a sphere. This is a portion of sphere. But note very important thing. What? The flux which is passing through this flat surface of the cone, the same flux is also passing through this curved surface. Why? Because whatever field lines, number of field lines crossing this flat surface, same number of field lines is crossing this surface also. It's a very important thing to note. This is the flat surface of the cone, like a circular disc, right? So whatever field lines are crossing this flat surface, same field lines are also crossing that. So the flux through this flat surface is same as flux through this. But anyway, how do we calculate flux? Let us consider this angle as solid angle. Do you know what is solid angle? Solid angle. Solid angle. Solid angle is defined as this spherical portion is, let us say, A, area divided by r square. Have you studied this solid angle in steradian? In steradian, in grade 11 you have studied, but you might have forgotten. It's like plane angle. How do you define plane angle? This is a circular arc. This is theta. This is the arc length, and this is the radius. So theta is equal to arc length by radius. This is what? This is plane angle. Plane angle in radian. In radian. Correct. This is plane angle in radian. And this is solid angle in steradian. Steradian is the unit of solid angle. So what is the solid angle of full sphere? What is the solid angle of full sphere? Can you tell me? What is the solid angle of this full sphere? How much? Solid angle of full sphere. Total area of this sphere divided by r square. What is the total area of a sphere? 4 pi r square divided by r square will become 4 pi. Correct? Right? This 4 pi is steradian. Steradian is written as STR. STR is the unit of solid angle. Okay. So now we know that if we are closing this full sphere, we know what is the flux, because full flux we know, total flux, full flux we know. Full flux is charge inside by epsilon naught. And for full flux means we are taking the full solid angle. So full solid angle means full flux. So this much solid angle means that much flux. Okay. So this is unitary method. Now you use unitary method. Okay. So full solid angle means full flux, and one solid angle means full flux by full solid angle, full flux by full solid angle, full flux by full solid angle. And a general solid angle means how much flux? This full flux, general solid angle means full flux by full solid angle multiplied with whatever solid angle you have. Okay, this will be the flux of that much portion. Okay, so now we got a very good formula that if you want to find flux for a given solid angle, you have to take this full flux by full solid angle into the given solid angle. Now let us substitute this. Full flux is charged by epsilon naught, charged by epsilon naught. Full flux is 4 pi. So this is what is the formula. Very good formula, very nice formula, we can use it. Okay, so flux through a given portion of a sphere, this is now a sphere I am taking, and suppose charge is here, the charge is at the center. So how much solid angle it is making, based on that we can calculate. Okay, we can calculate this. Let's take very simple question to understand this, and also before going into this question we should know the relation between solid angle and plane angle. Suppose this is a sphere and I am drawing a solid angle. Let us draw a solid angle like this, and as I already told that you have to draw a disc here. You will be drawing a disc, and let us consider that this is some angle theta. When you are joining this center of this disc and with this is making a plane angle theta. This plane angle and the solid angle are related. This plane angle and the solid angle are related. What is the relationship? Very important relationship. Note that 2 pi 1 minus cos theta. Okay. So solid angle and plane angle are related by this simple formula. Now let us take a very simple question. Very simple question. Suppose that there is a charge present here, and this charge, and there is a sphere, let us say, and let us say that you have cut this sphere like this. You have cut it like this, and you have cut in such a manner that this distance from this is equal to r by 2. Total radius is r, we know that total radius is r, but you have cut it from this point, you have cut it like this, so that this distance is r by 2. Now the question is that what is the flux through this surface? What is the flux through this portion? Or what is the flux through the flat disc which you will make here? You will make a disc here, right? What is the flux through this disc or this surface, because that is same. Very simple. How to do that? You have to find solid angle. To find solid angle you need to join this, and you want to find solid, but you need theta this. So to calculate solid angle you will use theta. What will be theta here? Note that this distance is how much? R by 2. This distance is r by 2 and this is r. So cos theta you can easily calculate. Cos theta is equal to r by 2 by r in this triangle, right? This is 90 degrees. So in this triangle cos theta is r by 2 by r. That means half. That means what? That means cos theta half. Directly use it. Calculate this solid angle. So 2 pi 1 minus cos theta half. That means 1 minus half into 2. That means pi. Cos theta you got this solid angle you got. Directly use this formula. What is the flux through this surface? Flux through this surface will be flux that we want to calculate through that is total charge by epsilon naught, that is the full flux multiplied by fraction of solid angle. This solid angle is pi, total solid angle is 4 pi, gain is over charge by 4 epsilon naught. Are you clear about this? Yes. Okay, so remember this is a very important formula, will be used in many problems. Okay, so done. This is, but then you can, I think, work out problems on this. You start working out. Worksheet already is given, right? 3 worksheets are there. Did you work out questions on this? First worksheet, it will be there questions, I think. Second, third, also some questions will be there. So start working on Gauss law. Next class we'll discuss out problems on this. Okay, fine. Okay, bye bye then.